Now, cracks, as you see here, are always a problem. It's water can seep through. It's not very aesthetic. But what is worse is this. If you are making a concrete slab and the concrete slab is shrinking, and then you're putting on the walls, which have not shrunk yet, and they are starting to shrink, then you will get some tensions into the wall. And finally, if the tensions are stronger than the concrete strengths, then you will get cracks. And if you get cracks and the concrete or is a cellar or is a parking lot under the earth and you have a lot of humidity, then you will see the ingress of water. And this is exactly what that picture is about. So just going shortly through the general consideration, OPC always shrinks. This is what we have learned, and it is true. New products like calcium sulfur aluminate do not shrink or do shrink less, but are much more expensive. With the OPC, this goes into cracks, and you need an anti-shrink agent, and we will propose different ones of you. Now, the mechanism of shrinkage is quite complicated. Once you pour your concrete and the surface is getting dry, you get micro cracks normally. If you can cure it or keep it wet on the surface, then these micro cracks will not appear. If they do appear, it's a weak point where later on with shrinkage, the cracks will develop into bigger cracks. Chemically speaking, autogeneous shrinkage is that the cement who takes up the water and uses it to make his hydrates will shrink to about 8% in volume. After the drying of your concrete, there is still some humidity in, and the humidity will go out of the concrete, and the pores will then shrink, and then you will have a shrinkage, which is a drying shrinkage. Thermal shrinkage, naturally, with the Chinese one who made a lot of dams, the temperature in a dam with cement can go up to 80-90 degrees, which is very hot. So it takes sometimes months for a dam to cool down. And naturally, like all materials, when material cools, you get some shrinkage. And then you have carbonation, which is the last possibility. So there are certain things you can do against it. You can cure it. You can use a low water cement ratio, which is today common standard. You can avoid wind and temperatures by covering your concrete, or you can wet your concrete surface. In the dry shrinkage, as it is in a late stage, you have no real possibilities. You can't keep an industrial floor wet for 6 months, so dry shrinkage will always happen. And this is one of the most strongest shrinkage you will get now. The biggest shrinkage occurs in the first week. The volume of the concrete decreases by about 8 volume%. You can imagine that it's quite a lot of thing, because the water is incorporated in the crystalline structure, and you get major pores in concrete anyway. Thermal shrinkage, well, as I told you, it can be over 80 degrees in massive concrete parts, and such construction may take months to cool down. I will not dwell on the carbonation shrinkage. The results is normally what we see here. There are cracks. Some water is passing through the cracks. It will dissolve the calcium hydroxide, which is then in the concrete, in the cement left, coming on the surface, and with the CO2 of the surface, it will carbonate on the surface and make calcium carbonate and have these white deposits. Or it will attack the steel, and the rust is always a bigger volume than the steel. Therefore, the moment that the steel is corroding, you will have a pressure on the concrete, and you will see that the concrete will fall off. You can see this by almost every bridge today. No? And that leads to costly repairs, naturally. So the best thing, evidently, is avoiding shrinkage altogether. That means using some expansive additive, which can help you to reduce the shrinkage, because if you reduce the shrinkage, then the tensions into your concrete will be lower, and therefore cracks will not appear. If you cannot do this, there is a possibility of using a self-healing concrete. That means some additive added to the concrete, which in the later stage will increase the volume of the concrete and close the cracks which have formed. We are using here magnesium oxide. We don't use bacteria. Magnesium oxide is quite a cheap mineral. It's a natural thing. It's not very, its regulation is almost not there. It's a mineral. Here are different pictures of crystals you can form. The ettringite, which we form with calcium silicate hydrates, are long needles normally. That means they are fixing the cement particles here in the space, therefore no shrinkage. Here you have magnesium oxide. Magnesium oxide is almost insoluble in water and is producing magnesium hydroxide, which is also almost insoluble in water. Therefore, what you will see in your concrete are these particles where the magnesium hydroxide crystals are growing on the magnesium oxide. This is a slow process because there is no dissolution, and the volume of the particle will at least double. And we can use mixers, naturally. So this is the chemical reaction. Normally, the expansion in concrete is known and is a dangerous thing because through experience, we know that after years, the concrete may break or get cracks through the expansion because of the doubling of the volume. And this is why it is limited. Looking at the production temperature, the usual magnesium oxide produced in Portland is produced at the Portland temperature, naturally at 1450, which means that the magnesium oxide is a sintered particle where the volumes are low, and the reaction is very slow because the surface is not very big. If we go down with temperature, at lower temperatures, we modify the grain size and we get something like a sponge with a high surface and a higher reactivity. This is to show you the difference. You can see here on the straight line, this is a dead burned magnesium oxide. It may be fine or it may be coarse. You see that it starts very slowly. It's a slow reaction, and you can see that after a year, this reaction goes on and on and on. And this is a dangerous type of magnesium oxide. Now, if you burn it at a lower temperature, then you get the blue curve. And the blue curve, you can see that your magnesium oxide is reacted after 150 days or 100 days, depending a bit on the reactivity of your magnesium oxide. And we have made these tests to show that there is no magnesium oxide left for the late expansion of the concrete. Therefore, there is no danger that you have a bad expansion after years. Here we substituted with 10%, which is quite a high amount. Normally you don't have to use so much. It is a slow reaction in any case. So now here we have exposed some prismas to the shrinkage and then to the dry air. And you can see the blue curve is the standard reference of a normal prisma. And you can see that in the beginning of the reaction, you have a sort of expansion which lasts for about, let us say, 10 to 20 days. And then your concrete will dry out and the magnesium oxide is not completely reacted. After 180 days, we put these specimens in water and to look what they are looking like and to see if the magnesium oxide, which is remaining in the concrete, is still reactive. So on the blue curve, you see you have a swelling of concrete. You always have a swelling of concrete when you put it into water because the pores will fill with water and it's like a sponge, it will expand. But what you see, for example, in the yellow curve on the top, is that you don't have only this expansion, but you see that you have something on top of it. That means that the magnesium oxide is reactivated. And if you look at 250 days, you can see that you have no tension in your concrete anymore. You are coming to a 0-0 level of your concrete. That means actually what you're doing here is you're putting an expanding additive into your concrete. It will remain partially not reacted. And later, if some water comes through a crack, then it will start to react again and will close the crack. Now, Lina Amar, which is named here, has made a thesis at the University of Rennes with both calcium silicate, calcium sulfoaluminate cement 10% or magnesium oxide at 5%. And you see that after 35 days, the cracks, which has been made on purpose, naturally, in this case, start to close. And at 120 days, the cracks disappear because the magnesium oxide or the calcium sulfoaluminate will react and make a new binder, which will then close the crack and give a good strength. Here we have an average healing rate. This is a calculation of a reference. You can see that with magnesium, because it is slow in the beginning, the healing rate is not very big, but after 25 days, the healing rate is as high as the concrete is normally, and it will continue naturally with time. Here we have 10% magnesium oxide, so here we have more expansion, and we have already at 7 days a higher expansion that we will have with the reference. Now, magnesium oxide, as we have seen before, uses only one molecule of water to double its volume. That is important because, as we mentioned before, we are working with reduced water in the future to get better strength. And a nitrogen molecule needs about 32% of water to get into ettringite. Which means that if you don't have enough water in your product, the reaction cannot happen. Magnesium oxide goes over 100 degrees, there's no problem, and the reaction ends after about 90 days. So where can you apply these? As I told before, the Chinese are making a lot of dams and water-containing constructions to avoid the cracks, which there could be a real danger for the environment. What people normally do is they put enormous amounts of steel into that. The steel will hold the cracked concrete together. But if the concrete doesn't crack, then you can start to replace a part of the steel. And the steel, 1 ton of steel is producing about 1.6 tons of CO2. That means if you reduce your rebars in concrete, you will also reduce your CO2 emission to the air. The parking lot we mentioned in the beginning, many parking lots are under the earth. Therefore, when water penetrates into the parking lot, it doesn't look nice, and it's a drag. Cellars is the same. We are using a lot of rebars just to have no cracks in the bottom of the cellars. And the Japanese, who are producing a lot of railways and U-tubes and things like that under the earth, and they have a sandy soil, need a lot of anti-crack material because they don't want to have their trains sitting in the water. And then we come back to the self-healing. One funny picture I found in the past was this one. Naturally, if you are having a parking lot, a lot of cars coming in with de-icing salts in the winter, and you have cracks, and these cracks go down to the rebar steel construction, the chlorine will start to eat up your metal parts, and the strength of your rebars will come down, and you may end like this one, where the top level just dropped down on the lower cars in the parking lot. Well, I thank you for your attention. I just flew over it. If you want further information, just write me at technical@newchem.org. We have 2 pages. One is the anti-shrink info, and the other one is a metaculin info. You will find a lot of information in there if you are interested. Thank you very much, and have a good day.